area on that, the magnetic property is not very well interpreted. Even magnetic property is measured, recorded in 1980 in ACC or some journals which probably not very attractive. Then these people have went back and looked at the magnetic properties of the complex which has been synthesized, and they find something very, very interesting, and then come back and report this one of the top journal for science.
Is quantum tunneling hypothesis or experiment as well?
I'll show you. It's experiment. That is why it's been launched in nature.
No, just quantum tunneling.
It's quantum tunneling. I'll show you this. Yeah, I'll show you this. It's a beautiful physics. Beautiful physics. So single molecule magnets are, why a single molecule magnet? It's a magnet, single molecule. You all know about bar magnets, right? Bar magnet we are using every day. In one way or another, we are exposed to that. That's a corrective spin. The spin is coming from enormous number of metal ions put together. Then you have a magnetic member, permanent magnetic dipole. But now I am talking about a molecule, one molecule which has permanent magnetic dipole, which is a magnet itself. One molecule as a magnet itself is a new concept. It's not known. So that is what is called, define this area, what is called a single molecule magnet. Why? How do we know that? Why this single molecule should be a magnet? First of all, to start with, what experiment one should do for it? That's what we will see. For example, the manganese 12, what they have done, individual arrows are representing a spin of the manganese 12. Assume that manganese 12 has a huge S around state. S equal to 5 we have seen, it has S equal to 10. That is of that. I'll tell you later on. And it has room temperature as usual. We start with random variation of spin of manganese 12. Then we cool with the applied field, this applied field, applying a field, and then everything aligns parallelly at low temperature, as we have seen before, no problem. What usually happens, as soon as you remove your magnetic field, everything goes back to the equilibrium immediately, because these are one-center things, so you just have to go there and then take the kinetic energy and bring back. That's all. But what has not happened here is that if you switch off the field, it does not go back. It just stays where it is. All the spins are still alive. If you maintain the temperature at 4 Kelvin, it still stays there forever. And
4 Kelvin, this is temperature of liquid helium, right?
Absolutely. That is where the bottleneck is.
So, in NMR, does every molecule behave as a single molecule magnet?
In NMR?
Yes. There also we use liquid helium and...
NMR is, we are talking about nuclear spin. Here this is electron spin. This is much bigger in scale.
Okay, but there would be this thing, right? A single molecule magnet.
No, overall it will not be there because that is where physics come in. So we need to see why it is not relaxing. I'll tell you next. In a few slides you will know why it is not relaxing. Then you will see. So for example, I have switching off the field, and then it slowly relaxes back. The relaxation time is about 3 months in 1.8 Kelvin. If I have 1 Kelvin, 50 years you can say it's right. Beautiful. So that's why it's called single molecule magnet. I can do the other way around. I can take the spin down, apply magnetic field downwards. I have the same thing. So the magnet is 12, randomly oriented, applying the field, putting them all in the same direction, switching off the field. Usually, if I am below the blocking temperature, which is what is called blocking temperature, we was asking about the field here, we are talking about a blocking temperature which is close to the equilibrium temperature or even less than equilibrium temperatures. So if I am maintaining the temperature from less than equilibrium, all the spins are pointing in the same direction. Why is it important? Why are we talking about all this? It is important because it can remember the direction that you are applying a field. I apply up, all the molecule remembers it, I apply it upwards, even after I switch off the magnetic field. It is important because I can then use these molecules to store information. How do I do it? I can apply a magnetic field up, I can convert that as binary 1, and apply a magnetic field down, I convert that as binary 0. These are the two numbers computer can understand. And I can read and write, no problem. So now I am doing a read and write in individual molecule at molecular scale. So you can then imagine what is happening. So we can tremendously increase the area density which I have talked about previously.
So, question. If the blocking temperature is what it is,
Yeah.
and the spins are kept there,
Yeah.
they are long half-life, that means there is a barrier for these things.
Absolutely. Yeah.
And that's my question: if the barrier is so large, how does it get magnetized in the first place?
That's right. All this are there. This is physics. As I said, you do the synthesis, you do the properties, then you go back and try to understand. So all these questions I'll answer in few minutes. So essentially you want to be happy, you have a manganese 12. This may not be the nice picture, but I want to just show you that our 90-degree groove, which I have told you before, works here as well. I'm just showing you only the manganese 4 plus, which are the inner side of the manganese 12. These are 90 degrees, so they are on ferromagnetic level. Downwards, all of them ferromagnetic level. So this is the structure of manganese 12, beautiful manganese 12. You have all the pink ions or manganese 3 plus and all the blue or manganese 4 plus, the mixed valence cluster. What do we have? We have a ferromagnetic coupling among all the manganese 3 plus, ferromagnetic again within the manganese 3, but anti-ferromagnetic between manganese 3 and manganese 4. Just like the iron phase cluster I told you, we need to calculate the spin ground state. How do we do it? 8 times 2 for manganese 3, 4 times 3 by 2 for manganese 4, 16 minus 6 I have is equal to 10. Beautiful. It's very simple, but remember that they tried 3-4 papers to find out what is the ground state of this molecule. All the concepts are simple after we know what it is. Right, so let's just go back a little faster. So what we are trying to look at now, we are just taking a little physics so that we can understand what's happening. We have an S equal to 10. Remember that this is the ground state of the molecule. We always have all the exact state is equal to 9, 8, 5, 4, 3, 0, 2. All this S equal to 10, right? So the 21 MS levels are there. Just like you have S equal to 1, plus or minus 1 and 0 are the MS levels, right? You have S equal to half, plus or minus half is the MS level. We have S equal to 10, huge number of MS levels are there, and that level is split in the magnetic field. If you apply magnetic field, they all split. Now what's happening? So remember again, simple theory, that there is also spin-orbit coupling. Right? What does it do? The spin-orbit coupling suggests that the molecules, the MS levels, are not always degenerate, even in the absence of field. What does it mean? If I have an S equal to 1, I have 3 levels, plus or minus 1 and 0. I suppose that they are degenerate, but they will not. They will be split by spin-orbit coupling, what is called a zero field splitting. So there will be always a separation between MS equals to 0 and plus or minus 1, even in the absence of magnetic field. This is what is called the magnetic anisotropy or zero field splitting, whatever we call it. So that is also present in this molecule. This is a beautiful interplay of spin and the anisotropy combined together to putting out this property. So now we are going to learn a little bit about zero field splitting. I'm not sure how many of you are already know. So I just thought to show you a little bit. If you have an S equal to 2, we know that we have a plus or minus 2 and 0, plus or minus 1. These are 5 MS level, 2s plus 1. So these will split even in the absence of magnetic field. I'm talking about in the zero field. So for example, this is the arrangement. These are the arguments. Minus 2, plus 2, minus 1, plus 1 and 0. So 0 will go there, plus or minus, minus 2 will be there, minus 1 and plus 2 will be there. This splitting, the gap between these two is 0. Right? If I have S equal to 1, plus or minus 1 and 0 will split, and the gap between these two is 0 splitting. Here I have, this gap is D, this is 4D, I need to scale this all that. So the barrier height when given a molecule, a single molecule magnet, then it is given by x squared times D. So that is the barrier height for the reorientation of magnetization. I will come back to it. So what happens now when we are talking about the zero field splitting? This is D equals to 0, no anisotropy present. All the 3 levels will be equal, just like any S equal to 1 state. If D is negative, plus or minus 1 comes down in energy. MS equals to 0 goes up in energy. This is how the energy levels look like. If the D is positive, this comes down, this goes up. So the sign of D is also important for single molecule magnet. It's not only the magnitude of E, which determines the gap between the two, the sign is also important. The negative D brings large MS value lower in energy, positively brings lowest MS value lower. So what happens to this one? This gives rise to what is called a double potential. How does it happen? It happens because I have a minus 10 here, minus 9 here, minus 8, minus 7. You can go all the way up. All these gaps are given by zero field splitting. As I have told you, zero field splitting is not there. All of them will have been just superimposed to on top of each other. So zero field splitting is split. This number of levels is given by S, as I said, 21 levels should be there. So this is the barrier. One level of up, another level of down. So the height of the barrier is determined by S squared times D. S equals to 10 here. Zero field splitting has been accurately determined in DPR spectroscopy will be minus 0.5, remember. So we are getting about MS squared times D. So 70 Kelvin. The 70 Kelvin, what does it tell? The manganese 12 behaves as a magnet below this temperature. Above the temperature, you have enough kinetic energy, you cannot see that material. That's what it is. This is what is called a theoretical blocking temperature for manganese 12. Okay, move on. Let's see what happens now. So, how do I know that this is a single molecule magnet? I like to measure the magnetic susceptibility, magnetization. So, manganese 12 is a hot magnet. If I keep the temperature at 2.1 Kelvin, I see this beautiful hysteresis loop. So, what does it mean? What does it tell us? What can you understand? Right, what I do now, I am applying a magnetic field, right? I'm starting from here, assume that I'm starting from here, and then just slowly applying a magnetic field. At a large magnetic field, everything saturates. Why it saturates? I told you. If I apply a large field, everything aligns along the field. There is nothing more to add to the environment. So that is the maximum you can get. So that is the saturation point. If the saturation point is reached, let's say about 3 Tesla after applying, and then I switch off my magnetic field. If I switch off, if it is not a single molecule magnet, it should come back to immediately the same one. But manganese 12 does not do. It takes time to relax. That traveling time, you see, just that blue arrow traveling is the time it takes to relax. Sometimes it will never relax, so you have to apply what called a corrosive field, a field on downwards to push it down. I'm just applying now to 1 Tesla field, pushing it down, right? I'm just pushing it down, and then it comes here. Now it is all down. I can apply a magnetic field downwards and saturate it again. So again I'm applying downwards, saturating it again. So again it takes time to relax. Again I apply a small corrosive field upward, and then it goes back. This is how I measure. I can also do it by temperature. I just have to wait for like 2 months to relax, which is not practical. So I have to just apply a corrosive field, bring it down, and find out. These two lines are not overlapping. That is why it's a hysteresis loop. This hysteresis loop comes from a single molecule. This I'll tell you this steps up important. So what happens now? What is this single molecule magnet? All that we are talking about? I told you this is nothing but a double potential. Plus or minus 10, plus or minus 9, plus or minus 8, all there. So we have to go from there. We have to climb all the way up, go to 0, and then comes back to the other one. Then only the magnetization is going to relax. Then only the magnetization is going to relax. If I apply a magnetic field, this is what will happen. Eventually, you are going to distort the wire. Why? If I apply a field up, minuses will be filled. Just like S equal to half, they are degenerate as soon as I apply a magnetic field. Minuses come down, pluses goes up. So one of them is going to come down, another is going to go up in energy. So then we have thermal activation. What do we do? We'll have to go from minus 10 to minus 9, minus 9 to minus 8, minus 8 to minus 7, minus 7 to minus 6. All the way the electron has to jump, with available thermal energy. It has to jump to the top of the hill and then comes down. That is nothing but, you can explain this relaxation with a simple Arrhenius equation. I'm sure of you have studied Arrhenius equation. Simple Arrhenius law just follows, you can get your relaxation done. Right? So this is the time it takes to relax. Two questions. Yeah.
You can see any tunneling splitting.
Yeah, I'm coming.
And I remember tunneling itself could be a phenomenon to take you from your field.
That's right. I'm coming to that. So I'm coming to that. So this is basically the application of field. So we have 50%, 50-50 possibility. Then we apply a magnetic field. One is more stabilized, one is more stabilized than the other. And then other field on the other side, the extreme side, we actually saturate. So this is the hysteresis that we are looking at from the perspective. Now the hysteresis loop again. Before we go into the tunneling and we'll be learning a little bit more in 10 minutes left. So you can actually speed the temperature. Right? So what is T as a hysteresis? I was showing you only one curve. The weight of the hysteresis is related to the temperature. Why? Because the temperature has thermal energy. If I increase the temperature, I have more thermal energy. It's going to relax fast. So you can see that as the temperature drops, for example, here I have 4 Kelvin, I have the narrowest coercive field. The coercive field is nothing but the gap between the two lines. So the narrowest here, and as the temperature drops, the coercive field increases. At 1.8 Kelvin, they are not even able to measure it. It takes like months to want to put the sample for months in a meter. Right? So 1.8 Kelvin. So the other option is to sweep the rate. What is the rate? Actually, instead of sweeping the temperature, I keep the temperature constant. I start sweeping the magnetic field up and down. Right? If I apply a magnetic field down, all molecules follow up. Right? Then immediately I'm switching it and changing the magnetic field down. Molecule takes time to relax. Right? It takes time to relax. It cannot go back immediately to the down. So by changing the sweep rate, the rate at which I apply the magnetic field, if I do it like 500 times a second, molecule will not relax. If I do it like 2 times a second, molecule has enough time to relax. So by sweeping the sweep rate, I can also increase the risk where the risk is. These are the 2 factors which are available by which you can find
If
this
you look at an electron that is slipping back and forth.
Yeah.
Why is that taking time?
That is exactly. The spin is correlated to the S level. The spin of the electron is correlated exactly to the barrier height I was telling you. Right? That is unusual. That is the unusual thing about this molecule. Spin of the electron doesn't take time. It should immediately happen. It does not happen because there are so many S levels out there, very unusual, 21 levels. And there is a large D, negative D, 0 to 50. All these levels are small. So it takes time. It's not a lot of time. Glaciation time is, we are talking about years only at 1.8 Kelvin. Okay? So it's not a lot of time. Right, this is the hysteresis loop. You can build your magnetic memory now if you want to do magnetic swell. It is still possible, but your computer has to work at 1.5 Kelvin. You know now where the advancement is. The advancement is required if you want to take these molecules to end user application.